In this video, we are going to discuss protecting groups. Now, in the last video, we talked about Grignard reagents. So let's say that we are performing the following reaction. 3, 4, 1, 2, 3, 4, just counting my carbons here. And let's say we want to react this with a Grignard reagent. What do you think our product will be? So according to our last lecture, we would typically expect that negative carbon in the Grignard reagent to attack the partially positive carbon on the carbonyl group. However, unfortunately, the alcohol is going to prevent that from happening. So this is a problem. And the problem is that the alcohol is too acidic. So our negative carbon can act as a base and will preferentially grab that hydrogen on the alcohol group. So we don't end up with a Grignard reaction like we would normally expect. And our product will give us a negative oxygen. And there's actually no reaction with the carbonyl carbon. Now, there is a way around this. So the solution is actually to use what's called a protecting group. So I'm just going to erase this and make some more room. But you can always rewind if you want to write those notes down in more detail. So our solution for this problem is, let's say we have an alcohol on our carbon chain, and we want to kind of block that alcohol from reacting with our Grignard reagent. We can use something called TMS, or trimethylsilane, and basically this looks like the following. We have a silicon atom bonded to 3 methyl groups and a chlorine. And this is what we call a protecting group. And I think your textbook gives this a different name. They call this trimethyl silyl chloride, but you can also call it trimethylsilane, that's fine. And we can abbreviate that TMS. All right, so what ends up happening is the oxygen on our alcohol performs backside attack, and that's going to cause the chlorine to leave. So this is an SN2 type reaction. Now, normally you might think, isn't that silicon atom kind of blocked by those methyl groups? Isn't that pretty bulky? Yes, but silicon is really large compared to, let's say, a carbon atom. So if that was a carbon atom bonded to those 3 methyl groups, then that probably would be too bulky to react with. But silicon is so much larger that any methyl groups don't really block it from being attacked. And your textbook actually has a nice picture showing how the silicon atom isn't really sterically hindered because it's so large. So let's just make a note of that. So backside attack is possible because silicon is larger than carbon. Okay, so what we end up forming is the following. So now oxygen is bonded to that silicon atom. It's bonded also to hydrogen and to the alkyl group off to the side, the R. Now, because oxygen is positively charged, we want to make it neutral, so we're going to use triethylamine. And the triethylamine is going to deprotonate the hydrogen. Or sorry, the oxygen. There we go. Okay, so now we have blocked oxygen, and it no longer has a hydrogen that the Grignard reagent can react with. So we've protected that oxygen. Now you could also write this in a different way. You could write this as the O bonded to TMS. So you can just use the abbreviation from above. But again, the main idea is that position is blocked. So the Grignard reagent can no longer react with that functional group. So there's no acidic protons. Okay, so let's look at an example. And we're going to use that same example that we saw earlier. So let's rewrite that starting material. So instead of starting with the Grignard reagent, we're going to take note of that hydrogen on the alcohol and say, oh, we can't use a Grignard reagent yet. We have to block that position from the Grignard reagent. So we're going to add a protecting group. So first we're going to add our trimethylsilane along with the triethylamine, which will deprotonate the oxygen. And then that will give us our protecting group. So you can write that as TMSO. Now we have the ability to attack the carbonyl carbon with a Grignard reagent. So let's add our Grignard reagent. And actually, I'm going to rewrite this methyl as CH3 minus, just so we can keep track. All right, so now our Grignard reagent can attack that carbonyl carbon like we normally would do. And now that oxygen is negatively charged, so we're going to add a hydrogen. And we can just use something simple like water to protonate the oxygen. Okay, so now we have our alcohol group, which is what we were trying to achieve by using the Grignard reagent. But how do we remove that protecting group? Well, there's a couple different ways that you can remove the protecting group and add the hydrogen back onto oxygen. So you can either use just a weak acid, or sorry, a dilute acid, not a weak acid, or something called tetrabutyl ammonium fluoride, or TBAF. So TBAF is quite large. It has a nitrogen in the middle, and it's surrounded by butyl groups, so 4 carbon chains. And it also has a fluoride ion that's hanging out. So the fluoride ion is really the important part here. All right, and we're not going to go over the mechanism for this, but you know, it's just good to know what these things look like. And I'll just circle the T-bath in blue down there. But this is going to remove the protecting group and add a hydrogen back on to that oxygen. So then we end up with our final product. So again, we took off this acidic hydrogen and replaced it with a protecting group. And then we could perform our reaction that we wanted to. And then we added the hydrogen back on at the end. And then the Grignard reagent is what added on to our product and gave us our alcohol group. All right. So this is just something to keep in mind if you are performing a reaction where you're trying to use a Grignard reagent. So if you're trying to form an alcohol, like a secondary or tertiary alcohol, just be aware that if there's another alcohol on the chain, the Grignard reagent's going to react with that instead. So you'll need to add a protecting group to make sure that you get the product you want at the end. All right, so we'll end this video here. Next time, we're going to go over some substitution and elimination reactions of alcohols. And some of it will be review, but there will be a couple of new reactions that we mix in there. So we'll talk about that next time.